There's a flexible urethane sealant sitting in hardware stores across the world right now for $3 to $8, and it does something a $10,000 procedure also does. It stops water from entering foundation cracks. Not almost as good. Not comparable. Measurably, provably better, because it does it before the damage compounds, which is the only window that matters. It prevents water infiltration. It reduces the soil expansion and contraction that grinds your foundation from below. It slows the progression of early-stage movement before it becomes structural. The American Society of Civil Engineers, across publications spanning 2010 to 2022, confirmed that moisture control is the primary prevention strategy for foundation damage from expansive soils. The Federal Emergency Management Agency, in homeowner guides published in 2011 and updated as recently as 2020, recommends drainage control and crack sealing to prevent water intrusion and stop damage from worsening. A $10 to $15 billion annual industry in the United States sells the alternative: steel piers, helical anchors, slabjacking, procedures that run from $5,000 to $40,000. They did not forget this existed. That would be an accident. They buried it. That was not an accident. It was a decision. This is the story of urethane crack sealant and what it does, and why the window to act early was never supposed to reach you. Welcome back to Science of Survival, where we open the vaults. Hit subscribe and the bell if you're not already in. Around 2600 BCE, in the city of Mohenjo-Daro, in what is now Pakistan, engineers were solving a problem that would not be named for another 4,000 years. The Indus Valley Civilization had built one of the ancient world's most densely populated urban centers on alluvial plains where the soil shifted, swelled, and shrank with every monsoon cycle. The threat was not dramatic, it was slow, incremental. Water entered structures, the ground moved beneath them, and buildings cracked from the base upward. The same sequence that happens in any city today, on any continent, in any material. What the builders of Mohenjo-Daro did was observe it, and then build around it. Archaeological excavations at the site have documented what can only be described as a city-scale drainage philosophy. Water was directed, channeled, moved away from structures through covered drains, brick-lined channels, and planned street gradients designed to carry runoff outward and downward away from the foundations that held the city up. They did not have a molecular understanding of montmorillonite clay. They had something more durable. They had watched what happened when water was allowed to stay close to a building, and they had watched what happened when it was not. They chose not to let it stay. The decision was architectural, it was intentional, it was documented in stone and brick, and archaeologists have spent decades reconstructing its sophistication. Roughly 2,000 years passed before anyone on the other side of the world formalized the same principle in writing. In Rome, around 100 BCE, a military engineer and architect named Marcus Vitruvius Pollio was compiling what would become De Architectura, 10 volumes of documented construction knowledge that survive to this day. Vitruvius was precise in a way that reads as almost contemporary. He documented the use of pozzolana, a volcanic ash mixed with lime and water, which produced a mortar with two properties that set Roman construction apart from everything around it: flexibility and moisture resistance. Roman structures built with this material did not crack along rigid joints under load. The mortar moved with the structure slightly, absorbing differential stress rather than transmitting it as fracture. And water finding these joints was not drawn into them by rigid capillary action. The material resisted. The buildings in Herculaneum, preserved under volcanic ash since 79 CE, show these joints intact after more than 2,000 years. Vitruvius did not know what a polymer was. He did not know what elongation at break meant as an engineering specification. He knew that certain materials behave differently when wet and under load, and he documented it so others would know too. Two civilizations. No contact between them. Separated by ocean, by centuries, by language, by everything except the problem. Both solved it the same way. Move the water away and seal the joint with something that moves. That is not coincidence. That is structural physics. The mechanism that Vitruvius observed and the Indus Valley engineers built against has a precise molecular name. The soil beneath and around most residential foundations contains clay minerals, particularly montmorillonite, a layered silicate that absorbs water between its crystalline layers and physically expands in volume. When the soil dries, those same layers contract. This cycle, hydration, expansion, desiccation, contraction, generates what engineers call differential settlement. The foundation does not move uniformly downward. It moves unevenly because the soil beneath different sections of the slab or footing receives different amounts of moisture at different times. The American Society of Civil Engineers has documented expansive soils as one of the leading causes of structural foundation damage in the United States. The forces are not dramatic in the short term. Over months and years, they are decisive. This is where urethane sealant becomes technically remarkable. A quality polyurethane crack sealant, products like Sikaflex, manufactured by Sika, or comparable formulations, achieves elongation at break values of 500 to 800%. That number means the cured material can stretch to 5 to 8 times its original length before it fails. A crack that cycles slightly wider in summer and slightly narrower in winter does not break the seal. The material moves with the crack. Acrylic caulk, the product most homeowners reach for instinctively because it is cheaper and easier to find, has a fraction of that elongation capacity. It cures rigid. The crack moves. The seal fails. Water enters. The cycle continues. The International Association of Certified Home Inspectors has stated clearly that hairline cracks are often cosmetic, but that monitoring and sealing prevents escalation, meaning there is a window of intervention and it closes. The drainage correction compounds the sealant's effectiveness in a way that cannot be separated. FEMA's guidance on water intrusion in residential structures specifically names downspout extension and soil grading as primary controls. When downspouts discharge water at the foundation perimeter, that water saturates the soil directly adjacent to the footing. Hydrostatic pressure builds against the exterior wall, and the expansive clay swells. The foundation is loaded from 2 directions simultaneously, from below and from the side. Extending a downspout 1.8 meters or 6 feet from the building perimeter reduces that localized saturation event dramatically. Grading the soil to drop a minimum of 15 centimeters over 3 meters away from the structure removes the standing water condition that feeds the cycle. Most people walk past this solution every single day without any idea what it can do. The ones who find out tend to make sure the people they care about find out too. So why is this not on the shelf card of every home improvement consultation in America? Why does no foundation inspector's report open with it? Here is what a $10 to $15 billion annual industry looks like. Ramjack. Ocean foundation repair, groundworks, basement systems, U.S. waterproofing. These companies exist because foundations fail. That is not an accusation. It is a description of their market. But the economics of that market create a specific and predictable distortion. You cannot patent urethane sealant. You cannot trademark the principle of grading soil away from a building. You cannot build a subscription model around a downspout extension. You cannot charge recurring fees for the act of sealing a 3mm crack before the water finds it. The total material cost of early intervention, sealant tube, caulking gun, downspout extension, is under 1,500 rupees, under $20. The structural intervention that early intervention prevents starts at $5,000 in the United States and runs past $40,000 for complex pier and anchor systems. The financial logic is not subtle. An industry built on remediation has no revenue model for prevention. Prevention does not generate the invoice. Prevention eliminates it. There is no regulatory body requiring foundation contractors to advise on early intervention before quoting structural work. There is no standard disclosure requirement. The homeowner arrives at the consultation already past the window because they were never told the window existed. That is not oversight. That is architecture, deliberate and sustained. Now, here is exactly what to do with urethane crack sealant and water management. In the correct sequence, with the correct materials, at the correct measurements. Step 1. Inspect. Look above door frames and window frames for diagonal cracks and along the base of interior walls. Use this threshold. A crack under 1 millimeter wide is monitoring territory only. Photograph it and return in 3 months. A crack between 1 and 5 millimeters wide is your intervention zone. This is what urethane sealant is designed for. A crack at 6 millimeters or wider means a structural engineer, not a sealant tube. Do not blur this threshold. Step 2, clean the crack completely. Use a stiff brush or compressed air to remove all dust, loose material, and debris from the full depth of the crack. The sealant bonds to the substrate. If it bonds to dust, it fails. No exceptions here. Step 3, apply polyurethane sealant. Not acrylic, not silicone. Brands like Sikaflex, Dr. Fixit polyurethane formulations, or DAP polyurethane sealants are available at local hardware markets, Home Depot, Lowe's, Amazon, and Flipkart in the 300 to 600 rupee range. Load the tube into a standard caulking gun available for 300 to 800 rupees. Fill the entire crack continuously from one end to the other without stopping. Smooth the surface with a wet finger immediately. Cure time is 24 to 48 hours. Do not expose the fresh sealant to rain during that window. Wear gloves throughout. Work in a ventilated area. Do not apply to a wet or damp surface. Moisture in the crack prevents adhesion. Watch for a slight surface skin forming within the first 2 hours. That is the process working. The full cure takes 24 to 48 hours, but that surface set confirms the sealant is bonding correctly. If you see no visible skin after 4 hours in normal conditions, check 3 things. The surface was wet when you applied it, the temperature was below 5 degrees Celsius, which slows cure dramatically, or you used an acrylic product by mistake. Check the tube. Polyurethane must say polyurethane. Step 4, and this is the step that determines whether step 3 lasts. water management. Extend every downspout at least 1.8 meters or 6 feet from the exterior wall using a rigid or flexible extension available for 150 to 500 rupees per unit. Then check your soil grade, walk the perimeter of your building and observe the direction water flows after rain. The soil must drop a minimum of 15 centimeters vertically over every 3 meters of horizontal distance away from the foundation. If it does not, if the ground is flat or slopes toward the building, add topsoil and regrade before the next monsoon cycle. The sealant manages the crack that already exists. The drainage correction prevents the next one from forming. Step 5. Monitor. Photograph every sealed crack at the time of application. Return every 3 months with a ruler. Measure. If the crack is growing past the sealed area, or if new cracks are appearing in a pattern, that is your signal to consult a structural engineer. The sealant is not a diagnosis. It is early intervention. It extends your decision window. For maximum safety, do not apply sealant and consider the matter resolved. The monitoring protocol is not optional. It is the mechanism by which you distinguish between a crack that is stabilized and one that is progressing. Without monitoring, you have sealed your ability to know. $3 to $8 in sealant and under $10 in drainage hardware, applied in the correct sequence versus a structural intervention that starts at $5,000. That is the decision the industry prefers you never get to make in the right order. Ancient builders at Mohenjo-Daro directed water away from their foundations 4,600 years ago. Vitruvius documented flexible, moisture-resistant bonding and writing that survived 2 millennia. A $10 to $15 billion industry built its entire revenue model on the moment after those principles were no longer applied in time. This knowledge did not disappear. Someone made sure it stayed buried. What else do you think got buried the same way? Drop it in the comments. If this video opens something for you, subscribe now. The next vault opens soon. What is inside is even heavier than this.